Estimating common sense scene composition on belief scene graphs. Objects in human-centric environments are typically arranged based on their functionality and interactions with other objects in the scene. For example, a sofa is usually placed in front of a TV. This concept, called common-sense scene composition, refers to the likelihood of objects being placed in certain locations based on their semantic class. Towards this end, we propose a method for common-sense scene composition estimation based on a novel neurosymbolic CC model approach, which incorporates a language-enabled spatial ontology, where the input is the set of location heat maps L double prime times O, and the output is the predicted set of location heat maps L hat. In this work, we build the spatial ontology by asking a large language model to generate the spatial relations that link room classes to object classes. This ontology is then appended as an object attribute into the nodes of the input graphs used at training time. The infusion of ontology knowledge into the CC model establishes a neurosymbolic approach that inherently learns common-sense room-object relations to refine the predicted per-class location heat map. The use of a CC model also facilitates to estimate the common-sense scene composition as a joint probability distribution rather than precise positions, which closer resembles human knowledge and reasoning. We do an experimental comparison of two models, the baseline that uses only the information present in the input graph and the enhanced neurosymbolic model. Overall, the predicted distribution of both models are fairly similar to the ground truth, with the base plus ontology model presenting slightly better performance. We tested our approach on the Boston Dynamics spot-legged robot with the goal to contrast the estimated common-sense scene composition with human common sense. The overall experiment design required the robot to traverse the environment and to generate a partial 3D scene graph, which is later converted into a belief scene graph, then enhanced using the proposed CC model to estimate the common-sense scene composition of the environment. The results of the experiment are presented as the voxel representations of the estimated location heat maps for one semantic of interest, alongside the ground truth location of the most relevant semantic. For room A, we can observe the general behavior in where the semantic of interest plant is generally placed in close proximity to the most relevant semantic window, being the most likely location the bottom left corner of the room where the presence of other objects is lesser. This room also shows one of the limitations of the proposed framework. The use of a fixed rectangle-shaped grid comes at the cost of optimality, since the framework will still process the voxels located outside the room. Different to the previous rooms, the semantic of interest stove is generally placed in mid-proximity to the most relevant semantic refrigerator, and the most likely location is at the middle point of the walls, indicating that stoves are rarely found in corners or besides a refrigerator. Thank you for your attention.